This illustration shows the gravitational waves thought to be produced by two orbiting white dwarf stars in a binary system called J0651, according to an August 2012 study. Credit NASA as predicted by Albert Einstein's theory of general relativity in 1916, a massive object like Earth distorts spacetime around it like a bowling ball dropped on a trampoline. The larger the object, the more that spacetime is distorted by that object. If a marble were circling around the bowling ball on the dimpled trampoline, the marble would fall inward, toward the bowling ball, like a rock in space circling a planet. Gravitational waves are ripples in spacetime that travel outward from a source. Video gravitational waves simply explained with a cube and a marble. Scientists think that powerful gravitational waves are created when two extremely dense objects, like two neutron stars, two black holes, or a black hole and a neutron star, orbit one another in binary pairs. The interaction of those two objects swirls spacetime, creating ripples that theoretically can be measured using powerful instrumentation. In the 20th century, researchers found indirect evidence of the existence of gravitational waves. That is, the researchers did not detect the waves directly, but instead observed the effects of those waves, but no direct detection was made. See images of gravitational waves. Gravitational waves are different from gravity waves, which are ripples created in the atmospheres of planets by the interactions of winds whipping over geological features on the planet's surface. In 2016, the Advanced LIGO Laser Interferometer Gravitational Wave Observatory announced the first-ever direct detection of gravitational waves. The discovery was met with excitement by both the general public and the scientific community. The announcement was made in February, but the actual detection was made in September 2015. LIGO scientists must perform lengthy statistical analyses of the instrument data in order to confirm a detection. A pair of black holes, weighing in at 29 and 36 times the mass of the Sun, merged into a single object, producing the ripples in spacetime that LIGO detected. The September signal was the first detection of binary black holes. Physicists Kip Thorne and Barry Barish of the California Institute of Technology and Rainer Weiss of the Massachusetts Institute of Technology received the 2017 Nobel Prize in Physics for their roles in the discovery. The LIGO team announced its detection of a second gravitational wave signal in June 2016. The pair of instruments detected the signal on December 26, 2015. The observatory announced a third detection in June 2017 and a fourth detection in September 2017. The first four gravitational wave signals detected by LIGO were all created by pairs of colliding black holes. The fourth detection was significant because it was also detected by the Virgo gravitational wave detector in Italy. Virgo is a collaboration between the National Center for Scientific Research (CNRS) in France and Italy's National Institute for Nuclear Physics (INFN). All of the black holes detected by LIGO are less than 50 times the mass of the Sun and are far from the largest black holes ever detected. The supermassive black hole at the center of the Milky Way weighs in at over 4 million times the mass of the Sun. The intermediate mass black holes are more challenging to explain than their larger siblings, scientists said. The 29 and 30+ solar masses come as an unusual surprise. If you look at most binary stars in the Milky Way galaxy, given the composition of the stars, we don't expect black holes of this mass. Vicky Calagera, a black hole scientist and LIGO team member, told Space.com soon after the first discovery. The higher mass tells us that these binary black holes formed from a particular environment with a metallicity that is different than the Sun's metallicity, she said. As LIGO and Virgo continue to study spacetime, and as more detectors come online such as one proposed by India, scientists will improve their understanding of intermediate black holes and black hole pairs. For every combination of masses and spins of black holes, you get a different signal, LIGO spokesperson Gabriela Gonzalez said during the 228th American Astronomical Society meeting in San Diego in June 2016. In 2012, California Institute of Technology Emeritus Professor of Physics Kip Thorne, a leading proponent of LIGO, predicted that the instrument would reveal a bounty of gravitational waves as researchers continue to improve the instruments and increase their sensitivity. We expect to see black holes colliding at a rate of perhaps somewhere between once an hour and once a year, Thorne said. In 2014, scientists with the background imaging of cosmic extragalactic polarization II experiment BICEP2 announced that they had found a faint signal in the cosmic microwave background CMB radiation that looked like evidence of gravitational waves created in the very early universe. According to the researchers, this discovery would have been smoking gun evidence for the hypothesis of cosmic inflation, which posits that right after the Big Bang 13.8 billion years ago, the universe underwent a period of incredibly rapid expansion. That expansion would have produced ripples in the CMB, the cosmic fog that fills the universe and represents the earliest detectable radiation. Unfortunately, the signal detected by BICEP2 could also be explained by dust in the Milky Way, and the researchers later withdrew the claim that they had detected gravitational waves. Video. Historic gravitational waves discovery explained by experts. CMB radiation came into existence about 380,000 years after the Big Bang. Scientists have mapped the CMB across the sky and found that it is a uniform temperature, evidence that bolsters cosmic inflation theory. Why the cosmic microwave background temperature is the same at different spots in the sky would be a mystery if it was not for inflation saying, "Well, our whole sky came from this tiny region." Chuck Bennett, principal investigator of NASA's Wilkinson Microwave Anisotropy Probe WMAP mission, told Space.com in 2013. So, the idea of inflation helps answer some of these mysteries, and it explains where these fluctuations came from. Additional reporting by Space.com staff and Nola Taylor-Read, Space.com contributor. Follow us at Space.com, Facebook and Google. Original article on Space.com.